In this optimization problem, we're finding the least expensive way to build a rectangular storage container with a given volume. The first step in solving this problem is to read through the problem carefully and find out what we're given and what we're asked to find. We are told that a rectangular storage container is to have a volume of 10 meters cubed. We're then told that the length of its base is twice the width. Material for the base cost $10 per square meter, and then material for the sides and lid cost $6 per square meter. We are to find the cost of materials for the least expensive container. Our second step is to put all this information into the 4 categories that I have listed here. I went ahead and drew a storage container, and now we just have to label the sides. We're told that the length is twice the width. So let's let our width be x, and then our length can be 2x. And then we'll go ahead and let the height be equal to y. Now we need to go ahead and write down these labels. You always want to label your variables. X is our width. 2x is our length. And then y is our height. Now what we want to do is find an equation that relates these variables and what we're given. We are told that our container is to have a volume of 10 meters cubed. So we can say that our volume is going to be the width times the length times the height. So that's 2x squared y, and that is equal to 10 meters cubed. Now let's see if we want to maximize or minimize something. We want to find the cost of the materials for the least expensive container. So that means we are going to minimize the cost. Let's write down the equation for our cost. I think this is the hardest part of the problem. Our cost is going to include the base, and that is 2x squared. And that is $10 because the base has to be stronger. So 10 times 2x squared. And then we're going to add on to that the sides. Let's do the front and the back first. That's this piece and that piece. That is XY, and we have 2 of them. And it is $6, so we have a 6 times 2XY. Now let's do the other 2 sides, this side and that side. Those are also 6. So we have 6, and that is 2xy, but there's 2 of them. So we have 2 times 2xy. And then we have the top, that is 2x squared, but it is $6. So we have a 6 times 2x squared. Now let's go ahead and let's simplify all this. Let's look at the x squared terms first. We have 20 and 12. So that gives us 32x squared. Now let's look at the xy terms. We have 12 and 4 times 6 is 24. So 24 and 12. And that gives us 36. So we have a 36 XY. Now we need to write this just in terms of x. So what we're going to do is we're going to go back to our equation for our volume, and we're going to find out what y is. Y is going to be 10 all divided by 2x squared. So we get that y is equal to 5 over x squared. Let's go ahead and substitute that in. Our cost is 32x squared plus 36 times x. And now we have 5 over x squared for y. We want to take the derivative of this function, so I'm going to rewrite it in the easiest way that we can take the derivative. And that's going to be c is equal to 32x squared plus 36 times 5. Let's see, 30 times 5 is 150, and then 5 times 6 is 30. So this is 180, and we have an x in the denominator. So we're going to write that as x to the minus 1. And there's our equation for our cost. Now let's think about our domain. We are told that the box has no limits on the length and the width, but we do know that x can't be 0 and it can't be negative. So we're going to say that x is greater than 0 and our domain is open, and we're going to need that in a few minutes. Our third step is to take the derivative of our cost function and find the critical values. Let's go ahead and let's write down c. It is 32x squared plus 180x to the minus 1. Now we can take the derivative. C prime is 2 times 32, which is 64x, minus 180x to the minus 2. Let's go ahead and let's simplify this. This is 64x minus 180 all over x squared. So let's go ahead and let's get a common denominator of x squared. In our numerator, we then have 64x cubed minus 180. I'm going to go ahead and highlight that because we're going to need that in a minute. To find the critical values, we have to set our numerator equal to 0. We're not going to worry about our denominator because that gives us x is 0 and our cost function isn't defined at 0. So we just have that 64x cubed minus 180 is equal to 0. So this gives us x cubed is 180 divided by 64. Let's see how we can simplify this. Let's divide both the top and bottom by 2. So this is 90 over 32. And we can divide the top and bottom again by 2. So this is 45 over 16. And we can't divide that any further. So we know that x then is going to be 45 over 16 to the 1/3. And we need to go back up and look at our units. It is in terms of meters. So we're going to put meters for x. Now we can go ahead and find our cost because that's what we want to minimize. Our cost right up here is 32x squared, and that is 45 over 16. Because it's squared, we have a 2/3. And then we have plus 180, and our x is 45 over 16, and it's to the minus 1. So this is minus 1/3. Now you get to throw that in your calculator, and when you do, you get a value. I'm going to put a dollar sign here because it's cost. We have $191.28. And let's go ahead and let's highlight that. Now, it may seem that we're done, but we're not. We need to justify that this cost is a minimum. To do that, we need to go back up to our interval. It is open right under the domain there. So that means we can use the first derivative test or the second derivative test. I highlighted our derivative in blue. It is complicated, so I don't think we want to take the derivative of that again. So for step 4, to justify our answer, we are going to use the first derivative test. And I'm just going to recopy our derivative because that's what we're going to need. We have 64x cubed minus 180, all divided by x squared. Because the denominator is positive, all we're going to be concerned about is the numerator, because we just need to find if c prime is positive or negative to the left and right of our critical number. Let's go ahead and let's draw a number line. We'll label this as x. We'll indicate that we have an open interval starting at 0, And let's put our critical point. It is 45 over 16 to the 1/3. At our critical point, the function that I highlighted in orange is equal to 0. So to the right of that critical point, we're really just concerned about our leading term, which is x cubed, and it is positive. So we know that c prime is going to be positive in this region, and then it's going to be negative in that region. This means that our function, which is our cost function, is going to be decreasing in this region and increasing in this region. And we can see that we then have a min at x is equal to our critical point. So let's write down that we have a min at x is equal to 45 over 16 to the 1/3. And we'll write down that c is equal to $191.28 is a minimum. We'll go ahead and we'll highlight that because that's really important. And now we can go to our last step, which is just to reread the problem and clearly state our final answer in a complete sentence. Let's go back up to and look at our problem. It says, find the cost of materials for the least expensive container. So our answer needs to be that the cost of the least expensive container is $191.28. And that's our final answer.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.